Okay, what's in the following course? I want to talk about lifelong learning. What is lifelong learning? If you Google lifelong learning, the one you are most likely to find is not related to machine learning. Lifelong learning. From its literal interpretation, you can know that lifelong learning refers to lifelong learning. That is to live and learn. So if you use lifelong learning as the keyword and Google it, what you usually find is the one about human. Lifelong learning for human. How do humans live and learn? Although the topic that everyone is paying attention to today is more about lifelong learning of human. However, in fact, the machine also needs to do lifelong learning. The method machines do lifelong learning is very close to the human imagination of AI. Before taking this course, before learning any machine learning contents, maybe your imagination of AI looks like this. We first teach the machine to do a certain thing. For example, learn to do speech recognition. And then it will do speech recognition. Next, you teach it the second task, image recognition. And then it will do image recognition. Then you teach it to do the third task, maybe a translation, and then it will be able to do image recognition plus voice recognition plus translation. You continue teaching it new skills. After it learns millions and tens of millions of skills, it becomes Skynet, and it can rule human. Most of us think about AI as that AI can continuously learn new tasks. And, finally, getting better and better, to the point that humans can't reach. The goal of this idea is lifelong learning. Lifelong learning is often abbreviated to 3L. LLL. Triple L. Not LOL but LLL. Lifelong learning has many other fancy names. For example, some people call it continuous learning. Some people call it never-ending learning. Sounds very fancy, right? There is a less fashionable name. Incremental learning. Okay, you might want to say, the goal of lifelong learning is too ambitious. I didn't want to make Skynet. What does lifelong learning mean to me? In the real application, lifelong learning is also useful. For example, you developed a certain model in the laboratory. You collect some information in the lab. Train with these materials. Train a model. After the model goes online, it will get feedback from the user. We hope that collecting information can become an automatic cycle. New data will be collected after our model is online. New information can let us update the parameters of our model. After the parameters of the model are updated, you can collect more information. After collecting more information, the parameters of the model can be updated again. Constantly update the parameters of the model. Our system will become more and more powerful eventually. You can think that the old data is the old task. The new data, which comes from user feedback, is a new task. In this scenario, it can also be seen as a problem of lifelong learning. The machine continuously collects data online and uses it to update model. It is a lifelong learning problem. What are the difficulties of lifelong learning? Don't we just let the machine keep collecting new data and update its parameters to achieve lifelong learning? Why lifelong learning is a topic worth studying? Here is a simple example. It will tell you what is the difficulty of lifelong learning. Suppose we now have two tasks. The first task is to recognize handwritten numbers. Give it a very noisy image. The machine has to recognize it as 0. Task 2 is also handwritten number recognition. But it is a relatively simple task. There is no noise in your image. We want the machine to learn these two tasks. So far, someone might say that they are not two tasks. They should be considered as a single task in different domains. It's okay if you think like this. You can also think them as a same task in different domains. But actually, here, I know that when I said that we want the machine to learn a series of tasks, you may think that let the machine learn speech recognition first, then image recognition, and then translation. But in fact, lifelong learning has not reached that level yet. In the papers of lifelong learning, the so-called different tasks are much like this example. They are like a task in different domains, instead of different tasks. But here, we treat them as different tasks, even if these tasks are very similar. When you are doing lifelong learning, You may have following problems. We will see them here. I have already trained a very simple network. It has only 3 layers. 50 neurons per layer. First it learns on task 1. After it finished learning, the result we got is like this. 90% accuracy on task 1. Even if it haven't learned task 2 yet. Task 2 has already got a 96% accuracy. The result of this transfer is very good. Being able to solve task 1. In fact, it can also solve task 2. Okay, once the task is learned, we let the same model continue learn on task 2. Saying, continue, here means that, when we are learning task 2, we don't let the machine learn from scratch. We don't let the machine train from random initialized parameters. We use the model that has been trained on task 1, and then use it to continuously train on task 2. Please pay attention. We use the same model to continuously train on the data from task 2. What will happen when we use the same model that has been trained on task 1 to train on the second task? This is the result. The accuracy of task 2 becomes higher. Because it already gets 96% without seeing the data of task 2. It will no doubt become better if it sees the data of task 2. Becomes 97%. The bad thing is that the machine forgets how to do task 1. It had a 90% accuracy on the original task. After learning task 2, it became only 80% correct on task 1. It forgets the skills it has learned in the past. Someone might think, it is not weird. The network is small. You ask it to learn task 2. And task 1 is learned in the past. The network's capacity is limited. It has limited brain capacity. So it forgets task 1 after finishing learning task 2. In another experiment, we put the data of task 1 and task 2 together. What will happen? Suppose we put the data of task 1 and task 2 together and train the network. The result looks like this. It get 89% correct on task 1 and 98% correct on task 2. For this network architecture, it can learn task 1 and task 2 together. Although it only has 50 neurons per layer, it is enough to get this accuracy on task 1 and task 2. We don't know why it will fail. If not learning task 1 and task 2 together. That is, the network learns task 1 and then learns task 2. When learning task 2, it forgets what it has learned in task 1. The network has enough capacity to learn 2 tasks. But when you make it learn sequentially, it can't remember old tasks. Okay, let me see if any classmates have questions. Some students asked if the teacher is broadcasting live at home. The answer is yes, I broadcast the live broadcast at home. Okay. Let's continue. The example I just gave is an example of image recognition. I'll give another example of natural language processing. The situation we just saw is not a special case. It is a common phenomenon. This example is QA. Question answering. Which is our homework 7. In homework 7, you make your machine read a document and ask it a question, and then it can answer the question. We are not using the data of homework 7. There is a simpler QA task. This QA task is called BABI, usually pronounced baby. Baby is a very early QA task. When people just started to study QA. When people just want to use deep learning to solve QA tasks. People think QA was too difficult. We felt very difficult solving QA tasks with the neural network or deep learning. So Facebook first defined 20 simple QA tasks. They are called baby. These QA tasks are not real QA tasks. If you compare baby and homework 7, you will find homework 7 is much harder than baby. Articles in baby are generated using certain rules. They are all generated using some fixed sentence templates. The questions are also generated with the fixed sentence templates. So baby is a very simple task. In fact, it looks like this. Mary gave the cake to Fred. Fred gave the cake to Bill. Bill gave the milk to Jeff. And ask you, who gave the cake to Fred? The answer is Mary. It's so easy. In the 15th task, it says, sheep are afraid of wolves. Cats are afraid of dogs. The mouse are afraid of the cats. If Gertrude is a sheep, then what is it afraid of? It's afraid of wolves. See? Piece of cake. As for such a simple question, you might feel that it won't be a problem for the network. The network can even solve homework 7. There is no way it can fail to answer such a simple question. However, several years ago, people were really shocked at making the model able to answer these easy questions. Okay, what we need to do next is to make the machine learn these 20 QA tasks sequentially. A general way to use Baby is to consider all the tasks as a training set, having the machine learn 20 tasks at the same time. Another way is to train a model for each task respectively, so each of the models has its own skill. Here, what I want to do is to place the 20 tasks in a row and sequentially train the model from the first task to the 20th task. See if it can learn all the 20 tasks. Here's the result. Just look at the correct rate of task 5. The vertical axis here is the correct rate, and the horizontal axis here is the process of learning all the tasks. From the previous example, we already know that task 5 is really simple. Alright, we let the machine learn task 1, and then task 2, task 3, and task 4. After learning these tasks, you can find that, for all the timestamp, the accuracy for task 5 is always 0. During the learning of tasks 1 to 4, the accuracy of task 5 is always 0. There is nothing to be surprised, since it hasn't learned task 5 yet. Thus, it doesn't know how to solve task 5. The machine is not to blame for the failure. How about the situation after learning task 5? What will happen? After learning task 5, the accuracy rise to 100%. That is because the model has seen the content of task 5. And the model thus knows how to solve the same task. The accuracy becomes 100%. However, if we continue to learn the remaining tasks, what will happen? The accuracy plummets. When the machine finishes learning task 6, the accuracy of the model on task 5 returns to 0%. After learning task 7, the accuracy of the model on task 5 is also 0%. Once the model learns a new task, the old tasks will be forgotten immediately. Then, you might think that maybe it's because the machine just doesn't have the capability of learning a few more tasks. In fact, it's not. The picture on the left just now shows the accuracy of task 5. We let the machine learn these 20 tasks sequentially. If we combine all the data of these 20 tasks together, what will it happen if the machine learns 20 tasks at the same time? The picture on the right is the result of the machine learning 20 tasks simultaneously. The vertical axis here is not the accuracy of a certain task, but the accuracy corresponding to 1. The accuracy corresponding to 1 represents the accuracy of the first task, the accuracy of the second task, the accuracy of the third task, and so on till the accuracy of the 20th task. You realize that when the machine learns 20 tasks at the same time, of course, some tasks are difficult. For example, the machine could not learn the 19th task. But it's possible for the machine to learn multiple tasks at the same time. There are several tasks where machines can get very high accuracy. But this is the situation of learning all tasks at the same time. When you let the machine learn them sequentially, it will learn the new things and forget the old things. The experiment on the right tells us that machines can learn multiple tasks, obviously. But when you let it learn task one by one, it just refuses to learn multiple tasks. It has the capability to master multiple tasks, but it refuses to do so. It's not that it can't do it. It's that it doesn't want to do, but not it can't do. So, you will realize that when the machine learns multiple tasks sequentially, it's like a person with a hole in his head. It's like the person on the left. When the new task comes in, the old thing comes out. It will never learn multiple skills. This situation is called catastrophic forgetting. In front of forgetting, we purposely add the adjective catastrophic, because forgetting will also happen in humans. So, it's not surprising that forgetting happens in machines. But, the degree of forgetting is too much in machines. Basically, it couldn't learn new skills. So, for this kind of forgetting, we add the adjective catastrophic in front of it, to remind us that this forgetting is not a normal forgetting, but it is a catastrophic forgetting. Okay, we have talked so much. Next, we will look at how to solve the problem of catastrophic forgetting, and how to make the machine learn multiple tasks sequentially. But, before discussing the techniques, you may have a question. You may ask that, wait a minute. Didn't we just see that combining all the data of multiple tasks together can make the machine learn multiple tasks? Combining all the data of multiple tasks together to learn them at the same time is called training of multitask. Multitask training. It can make the machine learn multiple tasks. For the question of lifelong learning, what's good for it to be investigated? You can think about it. We assume that we want to make machine learn the 1000th task. To prevent the machine from forgetting the previous 999 tasks, you must take the data of all the previous 999 tasks out, and then combine it with the 1000th task, which is all the data of these 1000 tasks, and train them all together, in order to make the machine learn 999 plus 1, totally 1000, tasks at the same time. But this may be problematic in practice. Because if we want the machine to learn the 1000th skill, and it needs data for the previous 999 tasks, that means that the machine needs to store all the data it has seen. It must save all the data so far. However, you may not have that much space to store the data at all. On the other hand, computation is also a problem. If we need to put the data for 1000 tasks together in order to train, the training time may be too long. The amount of data from the 1000 tasks may be too much. Your training time may be too long, and you can't make the machine learn multiple tasks. So if the machine must do multitask learning to be able to learn multiple tasks, it's like a student taking a new class. But before he takes the new class, he has to retake all the lessons he has taken in his life, and read all the textbooks he has read again to learn new tasks. Obviously, this is very inefficient, as the number of tasks you have to learn become larger and larger. Your training time will get longer and longer, and you need to store more and more data. So although multitask training allows the machine to learn multiple tasks, it is not the ultimate solution to lifelong learning. In the literature, multitask training is usually treated as the upper bound of lifelong learning. If we put all the data together, though this is an impractical approach when there are many tasks, but it allows the machine to learn multiple tasks. So putting all the tasks together for training, or multitask learning, is often regarded as the upper bound of lifelong learning. It is the result that lifelong learning cannot surpass. So when one is doing research on lifelong learning, the researcher will tend to run multitask training first, find out where the upper bound is, then look at lifelong learning to see if he can approximate this upper bound. Okay, let's see if any classmates have questions. Some students said, multitask learning is equivalent to letting the machine review the material. Of course, the performance is better. True. What we have to ask now is, under the premise that no reviewing is allowed, can it remember what it has seen before, instead of reviewing the old materials every time it's learning something new? Some students asked, is it because its loss is adjusted based on multiple tasks that there will be this kind of catastrophic forgetting? You could say so. We will explain how catastrophic forgetting occurs later. Some students said, learn separately and ensemble. I'll tell you later. Or the next slide will tell you what kind of problems there are if it learns separately. Some students said, is it because the model continues to learn and change the old parameters to bad ones, but didn't use the original loss to correct it back? Right. We will explain later. why catastrophic forgetting happens. But it's pretty close to what this classmate says. Okay, let's continue. The next slide is about why we don't just learn a new model for every task. Why are we so obsessed with the problem of lifelong learning? Why must one model learn multiple tasks? Why don't we learn a new model for each task? If we did learn a model for each task separately, it is true that the catastrophic forgetting problem would indeed be solved. However, here's the first problem we'll encounter. Suppose we want the machine to learn a lot of skills. Something like Skynet, for example. Skynet should have millions of skills. And after all, we can't have a model for every skill, right? With this method, you may not be able to save all the models. On the other hand, if we were to use different models for different tasks, the data between different tasks cannot be shared. It won't be able to learn things that can't be learned from a single task. And if you think about it, humans only have one brain. Yet the brain can learn many different tasks and keep on learning new skills. We don't need to store every task using a separate brain. So why can't machines do the same? This is the question that lifelong learning is trying to answer. Can one model learn multiple tasks? Okay, some of you might say that this sounds similar to transfer learning. Transfer learning mainly focuses on training the machine to do task 1 and transferring the skill learned in task 1 to task 2. Although both lifelong learning and transfer learning make the machine learn multiple tasks, their points of focus are different. In transfer learning, we care about whether the skills learned by the machine on the first task can be helpful for the second task. So, we only care about the performance of the second task. In lifelong learning, the main focus is whether the machine can still perform the first task after it has learned how to perform the second task. So, although lifelong learning and transfer learning both involve two tasks, the main focus of transfer learning is how well it can perform the second task, while the main focus of lifelong learning is how well it can perform the first task. Okay, before talking about the techniques of lifelong learning, let's talk about how to evaluate the performance of lifelong learning. Of course, before doing lifelong learning, we need to have some tasks for the machine to do one by one. However, if you take a look at the papers about lifelong learning nowadays, the tasks are often relatively simple. Here's a common setting. Task 1 is handwritten digit recognition. Task 2 is still handwritten digit recognition. However, these images in the second task look a bit like starry skies. What's that all about? These are the images we get by scrambling the digits in a particular pattern. So every task corresponds to a different permutation. But shuffling the permutation is quite complex. You can simply rotate the numbers. You can create a new task in which images are rotated clockwise or counterclockwise by 15 degrees. In that case, every image is still a number. They only differ by a rotation. You can still do lifelong learning with this kind of easier tasks. You can also have the machine distinguish 0 from 1 in the first task, 2 from 3 in the second task, 4 from 5 in the third task, and etc. But in this case, 0 belongs to the first class, 1 belongs to the first class, 2 belongs to the first class, 3 belongs to the second class, 4 belongs to the first class, and 5 belongs to the second class. So if you give it any odd number smaller than 6, either 5 or 3 or 1, the machine tells you that it belongs to the second class. On the other hand, 0, 2, 4 belongs to the first class. The homework assignment for lifelong learning is multiple choice questions. We do provide some code, and hopefully you run through all of the code once. But this time, we do not ask you to generate good results. You have to answer some questions based on the content of the code. One of the points giving questions is, how did TA define the tasks in the program? Oh, here is a question from a student. Let me answer it first. Is there any method that can impose constraints on the neural network, while not changing the parameters too much so that it can still remember how to do the old tasks? Great. This is exactly the commonly used solution for lifelong learning. You spoiled it. Okay, let's continue. I told you how to define a task sequence. Now we need to know how to evaluate the quality of a lifelong learning algorithm. Here is the answer. First, you have a sequence of tasks. Also, you have a set of randomly initialized parameters. Apply these parameters on all t tasks. Then, you can calculate t accuracies. Apply the parameters on the casting set of the tasks. Then you can obtain the accuracies. Next, let the model learn the first task. After that, calculate the accuracy of all t tasks again. Then you just repeat. Learn the second task and calculate accuracies again. Do the same for all the tasks and calculate the accuracies. You end up with a table like this. Next, you will use this table to judge the performance of a lifelong learning model. In this table, each value refers to the accuracy of the test data for a certain task. For each value in this table, there are two subscripts, namely I and j. The first subscript represents the correct rate after training the ith task. The second subscript refers to the correct rate on the jth task. For example, R21 means that the correct rate of task 1 after learning task 2. RT-12 means the correct rate of task 2 after learning task T-1. So, if we watched the accuracies, whose I is greater than j? What does that mean? I is the later task. J is the previous task. What we want to know is that the performance of task I after learning with the previous task j. Does it forget what it has learned on the past task? If we are looking at the R, whose I is less than j, what does that mean? It means that we just finished the task I and haven't learned task j yet. Is it possible that the machine learned by itself without a teacher to solve task j? What we need to see here is the transferability on new tasks that have not been seen. How is the transferability? The most common method of evaluating a lifelong learning system is to add up all the correct rate in the last row. You let your model learn all the tasks sequentially. After learning the last tasks, you can test all the previous tasks and calculate the correct rates. The average correct rate means the performance of your lifelong learning method. This value may be the highest because the model just learns on the task T. It should perform the best on the task T. For the previous tasks, your model will gradually forget. The first task may have been forgotten miserably or completely forgotten. Maybe the correct rate is close to 0. The second task might be slightly better. Its correct rate may be about 1 or 2%. Then average all of these correct rates. We can use it to evaluate the quality of a lifelong learning system. This is a common approach. There are other evaluation methods. There is an evaluation method called backward transfer. The backward transfer is to subtract two values, RT1 minus R11, RT2 minus R12, and so on. Then add up all the tasks and calculate the average. This value is backward transfer. RT1 minus R11, RT2 minus R12. What do they mean? They mean the difference between the correct rate of task 1, when your model finishes task 1, and the correct rate of task 1, after your model finished all the t tasks. The memory is still fresh when it finishes task 1. The correct rate is the highest at this time. As there are more and more tasks you learn, your correct rate will continue to decrease. How much will it decrease? So we subtract this 2R. It can be assessed how serious the level of forgetting is now. Because every time the machine sees a new task, the old tasks will be forgotten. You can think about it. RT1 is usually smaller than R11. RT2 is usually smaller than R22. So if you subtract R11 from RT1, subtracting R22 from RT2, the value you usually get is negative. so the value calculated by backward transfer is negative and less than 0. If you can propose a lifelong learning method that is so great that its backward transfer is positive, then you are very good. Because usually, the backward transfer is negative. If you say that, after the machine learns a new task, it can also do better on the original task one. After learning new tasks, it learns how to do better on the original task too. Then, the lifelong learning you proposed is very powerful. General lifelong learning can't do this. Usually, as long as this value is not too negative, it's already very powerful. Okay, there is another way of evaluation, called forward transfer. The forward transfer usually is not the focus of lifelong learning. The question forward transfer wants to ask is the following. I've watched a series of missions today. I am a bit stuck. I do not know why. My mouse is a bit stuck. But it doesn't matter. Let's see if the classmates have any problems. Okay, no one has problems. Okay, let's continue. Today, the question forward transfer want to ask is how much the machine has learned when only saw tasks other than a specific task. So when you are doing forward transfer, you just subtract RT-1T from R0T. What does it mean to subtract RT-1T from R0T? It means what results your model can learn when it only sees tasks T1 to T-1. It doesn't see the mission T. This is forward transfer. Okay, next, we are going to see the solution of lifelong learning.